Hi, I'm Martin McClure. It's very good to be back at ESUG after a few years of absence. I work for GemTalk Systems on the GemStone line of products. And many of you know about GemStone, but it is a Smalltalk implementation that has a tightly integrated object database, which basically allows many Smalltalk virtual machines to share a common image, which is transactionally merged, basically, with everybody's changes. And so you can have thousands of virtual machines running against the same image. You can have these running across hundreds of machines, and you can have an image that is much bigger than the memory of any machine. And all of our production customers, or almost all of them, are running this on Linux. And when you're running a production system, especially a large production system, these systems tend to run on large servers, which are pretty expensive. And you don't really want to spend more money than you have to do this. So this leads to some questions. And the questions I'm going to be dealing with today are those of those dealing with memory, like how much memory do I need to run this application? And am I almost running out of memory? And we hate this question because we really like our customers to be successful. So we try to give them information that will not lead to them having to ask this question. But there is this need for information about how memory management in GemStone works and how memory management in Linux also works, because it's based on that. So the internet says a lot of things about Linux memory management. And some of those things are true, actually. Some of them used to be true and aren't true anymore. And some of them were never true in the first place. And I'm going to attempt to give you some of the actual truth. We'll see how well I do. So we're only going to be wading in the shallows because I only have half an hour here. And it's much a deeper subject than that, all the little details in the corners. But you can get quite a ways with just the basic concepts. But I realized as I was rehearsing this talk this morning early that it's actually longer than half an hour. So I'm not going to be able to do quite as much explaining as I'd hoped, and we're going to kind of rush through some stuff. Talk to me later. I'll be here the rest of the week if there's anything you want more detail on. So memory management in GemStone is really shaped by the facilities that are given to it by the Linux kernel. And the memory facilities of the Linux kernel are very much shaped by the facilities of the hardware, specifically the memory management unit of the hardware. So let's take a look at what the hardware provides. All of my specific examples here are going to be on the x86-64 platform. Other platforms like ARM are very similar, but there's a few little details that are different. But all of this is going to be x86-64. So the main thing for our purposes today that the memory management unit provides is the ability to have page tables. And these page tables translate the virtual addresses that you use in user space. Your programs all deal in virtual addresses. You never see a physical address unless you're inside the kernel. And they translate those to physical addresses that then can be used by the hardware to access memory. So here's a diagram I stole from the AMD architecture manual. And we have in it the, so up here at the top, right, we've got a virtual address. Now, virtual addresses in x86-64, at least classically, are 48 bits, and the rest is just a sign extension. And down here, we've got a bunch of tables that translate that virtual address into a physical address. And you've got a set of these tables for each process, because processes don't share memory usually in Linux. They don't, well, in Linux, a thread and a process are really the same thing, but for our purposes, a process is one that doesn't share memory. So you've got a register which is set for that process when the kernel schedules that process in, and it has a physical address of some 4K chunk of memory. And then these 9 bits of the 9 top bits of the virtual address are used to index into that, find an 8-byte descriptor, which has some flag bits and then a pointer to another physical address, to another page table, which uses the next 9 bits, which indexes into that, which indexes into that, which indexes into that, which actually then has the physical address of a 4K page. And then the lower 12 bits of your virtual address are the address within the 4K page that you're looking for. So here we've got, for each process, we've got one 4K table, up to 512 4K tables, up to many, many, and many, many, many tables, if they were all actually in use. I believe I calculated, if I got this right, that it would be, you'd have 512. Oh, that's right. I don't have power on, so it's dimming my screen for me. How nice. So it's you'd have 512 gigabytes of just page table memory for each process. So fortunately, you only have the ones that you need. There's a bit that says, there's nothing here, and so don't bother looking any further. So also, lookups through this are pretty slow. You know, memory access, as we saw in some of the talks over in IWST today, are pretty slow. Memory access time compared to the processing execution or processing instructions. It's you know, memory access can be the limiting factor in many applications. And if every time you want to access a piece of memory, it has to go, oh, well, I need to access this, and then I need to access that, and then I need to access that, and then I need to access that, and then I can access my memory. That's 5 times the cost. So fortunately, you don't have to do that a lot of the time. This is called a page walk. And there's a thing called the TLB, the translation look-aside buffer, and a couple of other little other structures in hardware that keep a hardware cache of recently done lookups. So it can say, oh yeah, we've got some stuff here that looks familiar, so I can now very quickly, without doing a page walk, I can do that translation. But the TLBs are small. There's not that many entries. So, you know, if you're accessing a lot of different areas of memory, you're going to have to do page walks. And we'll be looking at that more on. So there's other tricks you can do here, and one of them is what if we were to leave out the bottom table? We'd get something like this, where you only have 3 levels of table, and you now have a 21 lower bits that are indexing into a page which is 2 megabytes in size. And if you leave out one more, you have a 30-bit offset into a 1 gigabyte page. And this is great in many ways, in that you only have two table levels to walk through to get there. But there are potential problems with that, in that depending on which page size you use, it has to, if you ask for a certain amount of memory in a particular page size, it rounds up to the nearest page size boundary in order to allocate that for you. And if you're only wanting a few K of memory and you ask for it in a 1 gigabyte page, you're going to get a gigabyte of memory, which you probably didn't want. Also, newer servers, as systems with multiple terabytes of RAM are becoming available, this 48-bit address with 256 terabytes of address space started looking cramped. So the more recent chips have actually added a fifth table, and they use those higher bits of the, so now you have 512 times the amount of virtual address space that you did, but you also have an extra level of table to walk through. But you do have your 2 megabyte and your 1 gigabyte page sizes as well. And I fully expect that we will see the day when there is a 512 gigabyte page size. We'll see if that comes about or not. Okay, so that's what the hardware contributes. Let's see what the Linux kernel gives us. So basically, it comes down to allocating memory and deallocating memory. So let's start with how we allocate memory. Different languages have different ways of allocating memory. In C, you call malloc. In Smalltalk, you send the new message. But by the time that gets to the kernel, there's only about 2 or 3 kernel calls that will actually allocate memory. And internal to the kernel, as far as I can tell, it all boils down to one, which is mmap, which is memory map, which is the manipulating those tables that we just looked at. So you've got a couple of there's a value add that the kernel gives you in that your mmap can be either file-backed or it can be anonymous, which just means not file-backed. So that means, is your memory initialized to zeros, or is it initialized to the contents of some portion of some file, essentially? Also, you can get private or shared. Private is what most people consider normal. Shared means the semantics are somewhat different. And you get these four different options. File-back shared isn't used very often. That means that if you modify the memory area, the change is actually written back to the file. That's not used in Smalltalk very often. File-backed private things, your executables and your shared libraries tend to be mapped in that way. And this is what you normally think of as memory I have allocated for my own use, and this is shared memory areas. So let's take a quick look at some maps here. Okay. So here I've got a process running, and I'm going to, and I know it's PID. Can you read that from the back? Okay. So I'm going to look at this file that the kernel, this pseudo file that the kernel makes available. It shows everything that's mapped. This is an extremely simple program, the shortest one of these things you'll ever see, probably. So here we've got file names, file paths, because they're file-backed allocations. And anything that's blank over there is an anonymous mapping. And the heap is kind of a special case anonymous mapping because the kernel, for legacy Unix reasons, handles that a little differently. And here you've got 2 libraries that are loaded. We've got the dynamic loader itself. We've got the C runtime library, and we've got our program. In this case, there happen to be 5 mappings for every one. We've got 1 for each that is readable and executable. We've got 1 that is read-write. That is going to be the initialized data that is read in but is writable, so you can change it. But it's private. The P there is for private, so it's not going to be written back to the file if you modify it. And in this case, there's 3 different sections that are 3 different mappings that are read-only, that are just data from the file. The number of these things varies from like 3 to 5 in what I've seen. It really depends on which linker you use and what version of the linker. I think if you look at Faro programs, you'll see that they are, Faro VMs, there's going to be 3. But it's really the number of those read-only ones that varies. And we also have, they provide us a stack, and then there's a couple of areas here that are ways that we can cheat and communicate with the kernel a little faster for really common calls, like what's the time? So there's that. We also have this thing called SMAPs. And this is basically for every line in that file, it gives you all of these individual breakdown of how it's set up. And in so let's look at some of the mappings for libc. And okay, so here we see that that's a mapping of that's 1440K, but resident in memory is only 836K. So why is that? And the answer is that the kernel tries to do things lazily. It's like you ask for this much memory, it says, okay, I will give you that much memory, but it hides from you the fact that it doesn't actually give you the memory until you try to access it. So in this case, we've said, I want to map this section of the file, but we haven't actually read from all of those sections of the file because that's all the executable code of libc. And we've only done a couple of things with libc because all that program does is ask for what its process ID is, print its process ID, and then go to sleep. So it's made a very small dent, and it's only loaded the executable pages for that code. And there's also this zero-page thing that I won't talk too much about. It's just that for anonymous mappings, you're really all mapped to the zero page. So if you read from them, they'll be mapped to the zero page. And if you write them, then they become something else. And yeah, let's take a second look at that. Because there's one other thing I want to show you in there, is that this 836K is marked shared clean. But here, from the little p on this up there, we know it was requested as a private mapping. And that's the semantics, but it's showing up as shared. So you have to be careful about that word shared. So the one shared is what semantics you are asking for when you mmap, and the other shared in those things is it in fact shared? Because that was a mapping of the part of the executable code from libc. Now, there are other programs running on this machine that are also mapping libc. And because those areas are read-only, it's using the same physical RAM for all of the copies of that. So it's in actuality shared, even though you didn't request shared. So so when you're looking at the stats on your system, you have to watch out for that. Copy on write, I think I'm going to skip on that. Basically, if you read from an anonymous mapping, you're going to get 0. And if you write to it, then it's going to say, oh, I need to copy that 0 to a new page of physical memory, and then you can write to it. And if it's a file-based mapping and it's not shared, then when you write to it, it'll say, oh, well, I can't write to that shared region that other people are using. I'm going to make a copy of this and do that. But that's another way in which it's lazy. Doesn't want to allocate memory unless it really needs to. I'm not going to show you the Faro maps. They look similar, except that there's more anonymous mappings for where the image lives in memory. And then there's like a whole lot more libraries loaded. So in GemStone, GemStone's a little different in that the architecture of GemStone uses shared memory. So So we have, so on each machine on which it's running, there's this shared page cache, which is a subset, hopefully your entire working set, of your persistent objects that live on disk. And then you have a bunch of VMs. I've only shown 7 here, but it could be, dozens on one machine and hundreds on across many machines. And each of those VMs has its own private memory, plus it's also attached and looking at the shared page cache. So there's this feature in the Linux kernel that's called huge pages, and it is really just Linux's name for using those pages that are larger than 4K. And it's no coincidence that the sizes that are available on the x86-64 platform are 4K, 2 meg, and 1 gig, because we saw the hardware tables that dictate that. And there's 2 ways in the Linux kernel to get huge pages. The older way is the reserved huge pages. This is a region of memory that's actually set aside for huge page use that can't be used for smaller pages. And typically, and I call them reserved huge pages, it's because they're typically set aside at boot time, because if you try to set them aside later, the kernel is not guaranteed to be able to find you a contiguous set of RAM big enough to put the region you want. In fact, I've rarely seen it actually work after boot time. So usually it's set aside at boot time. And those can be either 2 megabytes or 1 gigabyte in size. Then there's a newer feature in the kernel called transparent huge pages, where a kernel thread will go around looking at the memory usage of processes, and if they've allocated larger chunks of RAM that would fit in 2 megabyte pages, typically not 1 gigabyte pages for transparent huge pages. But if you've done that, then it can actually like shuffle the memory around. It'll say, oh, I'm going to copy all of those things into a single 2 megabyte page, and then change the mapping table to point to that, and then you get the benefits of that. But there's work to do in finding the ones that are candidates, and there is, of course, a lot of memory accesses in actually moving the page. So it's fairly easy to lose that game because there's a lot of, if you're just going to do it for a little while and not continue using it, then you won't have time to pay back the cost of setting it up in the first place. And we'll talk a little more about that with GemStone a little later. So that's the story of allocating memory. Let's talk about how memory gets deallocated. So here is top running on this system, and this is one of your useful pieces of information about a system. So you can say, well, how much memory am I using? Well, here's what I've got. I've got 64 gigs of RAM on this machine. And here is what is actually free, about 3 gigs free. Okay, so almost no free memory. So that must mean I'm using a lot, right? Well, I'm not. I'm hardly running anything on this laptop right now. A better number to look at is this available memory thing. Now, Linux didn't used to have that. It's much easier to tell what's going on in your system now that this available memory thing is available. And but why is there this discrepancy between those things? And that is because, once again, just like with allocating, it is lazy about deallocating. For file-based mappings in particular. What triggers deallocation is when it feels memory pressure. If it says, well, I'm feeling like I don't have enough free space. So it wants to eliminate the least frequently used memory. And the hardware makes available statistics to the kernel that tells it how recently each page was accessed And those are some flag bits in those page tables that the kernel can read. And if you have file-based mappings that are clean, as in they haven't been modified, they're read-only or haven't been written to, those can just be dropped. So those are cheap to get rid of because you can always reread them from the disk if you need to. But you don't want to drop just anything. You want to drop the least frequently used ones. Anonymous mappings or file-based mappings that are dirty, those, in order to remove those from memory, you'd have to write them to swap. And I want to defend swap a little bit because it's got a bad reputation in the old days when we would see machines just swapping in death. But swap is actually a valuable thing if it's not overused. A good amount of swap to have for a general purpose system, and of course this varies on an application basis, but on servers that are running a mixture of things, I've found that you can have like swap the size of 20 to 25% of your RAM and have it pretty full, and the swap-in rate is very low. And if the swap-in rate is low, then you know that you're not losing a lot of performance because it's pushed things out that are actually not being needed. Because if they were being needed, your swap-in rate would be higher. And if you don't have enough swap, the system is going to be forced to push out more frequently used file-based mappings. And you want the least frequent stuff to be pushed out. So having some swap is a good thing. How do you tell what your swap-in rate is? There's one way is a utility called IOTop. There's a version of it that's in, the original version was in Python. There's a C version called, that package name is IOTop C on some distros anyway. And it can give you the swap-in rate. And then, if you're feeling memory pressure and it's dropped what it can drop on the floor, and that available memory stat that we saw in top, that is how much memory can you use without going to swap. But if you use all that up and you use up your swap and you're really out of memory, what happens? There's a thing in the kernel called the killer, the out-of-memory killer, and the out-of-memory killer will select a process, and it tends to be the process that is using the most memory because it thinks something's gone into infinite recursion, et cetera, et cetera. And it thinks, oh, that's probably the culprit, so I'm just going to shoot it in the foot, and it goes away. In a GemStone system, the things that are using the most memory are often the most valuable central processes that if you take those down, then all the VMs have to go down because they're relying on them. You'd rather have the killer. You really don't want to get into this situation at all, but if you do get into the situation, you would rather have it kill a VM or two to get a little more memory to use than kill a central process and bring your entire application down. So GemStone has ways of resetting the out-of-memory score for certain processes. And I don't have time to go into the details of that, but it's in the manual, and it's probably a good thing to do for a production application, even though it's not foolproof. It can still choose the wrong processes, even if the scores have been adjusted. Okay, well, let's quickly talk about just a couple of practices for GemStone. I'm almost out of time. But, so you have to look at how much memory for your shared page cache versus how much memory for the VM private VM memories. For the shared page cache, you want the working set of all the VMs on your machine. to be in there. For each VM, you want the working set of the objects that it tends to work with, ideally. How do you tell what the working set size is? It's application dependent. It's hard. Guess a size, run stuff, get statistics, analyze statistics. I cannot emphasize that enough. Try different things, and when you start seeing things like pages being read a lot, you're probably too small. More is always better, except you don't want to spend a huge amount of money. Huge pages. Use reserved huge pages for your shared page cache. If you're just developing on your laptop and you don't have a big repository, you can probably get away without that. But every production machine should be doing this. If your shared page cache is less than 10 gig, you can probably use 2 megabyte pages. If you're over 10 gig, use 1 gig huge pages. Use the transparent huge pages. Enable that for the VM's private memory. There's a setting where transparent huge pages are only used for those applications that say, hey, I advise you to use transparent huge pages, and we do that for the private memory in the VMs. And what happens if you don't use huge pages? Well, remember this? And I talked about how you've got, you could have 512 gigabytes of pages if you use too many. I was at a customer site, and they had just brought in a new server, which had 512 gigabytes of RAM. This was about a decade ago, so that was a very big machine at the time. And their application ran for a while, but the memory usage kept growing. Why did it keep growing? We weren't leaking memory. It's Linux being lazy about the allocation. And when they started running out of memory, I looked at the memory statistics, and they had 256 gigabytes of page tables because they had 3,000 processes attached to a 100 gig shared page cache, and those were being mapped lazily as it went on. The solution was to do what we had advised them to do in the first place, which was use huge pages, because you cut that by a factor of 512 for 2 megabyte pages and a further factor of 512 with 1 gig pages. And we also reduced the number of processes that attach to the shared page cache. So it's a solved problem now, but really, really do that. Because and it's also faster because you only have the 2 levels to walk through when you access things. So it's going to improve your performance beyond the not using as much memory. So what tools do we have? There's top, we looked at procmeminfo, that is system-wide memory statistics. SMEM, I highly recommend this. It's not in most installations by default. Most distros have it available though. Gives you better statistics than most of the things. StatMonitor and VSD are GemStone specific tools, but you can use them to monitor system statistics even if you don't use GemStone. And they will give you graphs over time of every statistic in procmeminfo. If you just cat procmeminfo, you just get a snapshot of that particular time. So you can gather the statistics of that. And that is it. Do we have any questions?
For one question, if there is any.
Okay, good, because I didn't have any answers. No, if you seriously, if you have questions, talk to me some other time. I'll be here all week.
Thank you very much again.